This right here is a little T-grip handle on the International Space Station. And when you give it a little twirl like that and just let it float freely, it flip-flops back and forth between two different rotations. And the reason for that has to do with the amount of rotational inertia it has. And I'm not going to explain why it does it just yet, but I will explain it here shortly. I should say that rotational inertia and moment of inertia are the same thing, that you'll hear me talk about it both ways. Well, before we get into rotational inertia, let's talk briefly and remind ourselves about linear inertia. It's just an object's resistance to acceleration. So if I had an object here and I put a force on it, it's going to accelerate, but the more and more mass it has, the more it resists that acceleration. Similarly, rotational inertia is also going to be an object's resistance to acceleration, but it's a different kind of acceleration. It's an object's resistance to angular acceleration. So if we had this object here and we put a force that would cause it to rotate, it's going to resist rotating, and that would either resist rotating faster, rotating slower, or rotating in a different direction, all of which would be a rotational inertia or moment of inertia. And there's a neat demo that you can do with just PVC pipes, and you hide what is on the inside of these things. So they both have the same mass, and if they have the same amount of mass, then absolutely they're going to have the same amount of inertia. So if you shake them back and forth, they will resist accelerating left and right to the same degree. But they will have different amounts of rotational inertia, and that's because on the inside of this I embedded a steel rod, about 12 inches of steel rod here, concentrated in its center, and here I had 6 inches on the end and 6 inches on the end. So they had the same mass, but where that mass was located gave it different amounts of rotational inertia. This one's going to be very easy to accelerate angularly back and forth, and this one's going to resist accelerating angularly back and forth. And again, it has to do with how far that mass is from the pivot point, or where that mass is distributed. It's interesting that a sphere, a disk, and a ring, if you drop them, they all accelerate at exactly the same rate. That's not because the force of gravity is the same on each of those three objects, but the ratio of how much force is put on it to how much mass it has produces the acceleration. And we recognize that as Newton's second law. So the acceleration is the ratio of the sum of the forces divided by the mass, or you could say it's how much the object weighs divided by how much inertia it has. And if it were a really light object, it would weigh very little, but it would also have very little inertia. If it was a real heavy object, it would have a lot of weight and also a lot of inertia. But the ratio of those produced the same acceleration for all of those. You drop a sphere, a disk, and a ring, they accelerate at the same rate. But that's not true if you put it on a ramp and let it go. If you let all three of those go at the same time, the sphere is going to get out ahead of the disk, and the disk is going to get out ahead of the ring. They don't accelerate at the same rate when they're rotating. They would drop at the same rate because the weight of them divided by how much inertia it has was the same for all three objects. But there's something different about the ratio of the two things that produces a different acceleration down this ramp. And that's what we want to talk about now. First of all, if I had two spheres, a large one and a small one, two disks, a large one and a smaller one, two rings, a large one and a smaller one, and they are different sizes, they have different masses, but these two shapes are the same, those two shapes are the same, and those two shapes are the same. As long as they are the same shape, they will race neck and neck the whole way. The two spheres do the same, the two disks do the same, and the two rings do the same. But if I race a sphere against a disk against a ring, invariably the sphere will get out ahead and the ring will always be the slowest. Okay, so something's different about that. And let's see if we can look at the different shapes and decide what is different. So here we have our sphere, disk, and a ring. And to help us see what it is about the shape, we're going to take the cross-sectional area. We're going to slice it right down the middle here. When we take a sphere and slice it down the middle, we expose a circle. The disk is going to expose a rectangle, and the ring is just going to have a little piece here and a little piece down there. We'll expose two little rectangles. And this is the axis that these are rotating about. All three of these shapes would be rotating away from us because of my arrows showing there. But let's see how the mass is distributed. With the ring, all the mass that it has is really far from the axis of rotation. Here, the mass is kind of evenly distributed from the center out to the rim. So maybe on average, it's, well, I don't know, halfway out. But for the sphere, it's really wide right along its axis of rotation, so there's a lot of mass right along the axis. And the further you go out, the less mass there is. So on average, it's not going to be right there in the middle because this had an even distribution. This had more mass along the axis and less mass out. So on average, the mass is going to be a little closer in. And through the use of calculus, you can actually come up with an equation to explain how much rotational inertia the object has. And I'm not going to derive this for you. We're not going to do the calculus. But I is for rotational inertia. It has to do with three things: how much mass the object has, the size or the radius, and then the shape of the object. For a sphere, the coefficient out in front here is 2/5, which means on average the mass is about 2/5 the way out from the center. If I did the same thing to calculate how much rotational inertia the disk had, what do you think the number out in front would be? Well, probably 1/2, because it was evenly distributed out. On average is just half the way out. And if this was half, what do you think the coefficient for a ring would be? Well, it would just be a 1, and I'm not even putting it because you don't usually put a coefficient of 1. But still, the amount of rotational inertia the ring has is going to be dependent on its mass and its size and its shape. There's just a 1 there. So let's just compare these two. 2/5 is the same thing as 4/10. 1/2, the same thing as 5/10. And 1 is just the same thing as 10/10. So when we raced these three different shapes down the ramp, the sphere was first every time. The ring was the disk was a close second, and you can see that that fraction has a little less rotational inertia than this. That's if we kept the mass and the radius all the same. And then the ring was always dead last because that has like twice as much as this if the mass and the radius are the same. But we also found out that they would race the same regardless of the mass and regardless of the size. So we have to explain that now as well. So this has a different mass and a different size than this, but they still raced the same. Before I get into that, I want to just give you a few other equations. This was the equation to calculate how much rotational inertia a sphere has, a disk has, and a ring, but we could take an object like a stick or a pipe, and if we hold it right here at the end and try to rotate it back and forth, we're going to feel inertia. We're going to feel resistance. If we hold it in the middle and try to rotate it back and forth, the mass is distributed a little differently, so we would feel a different amount of inertia. The equation to calculate the inertia of a stick pivoting on its end is 1/3 the mass of that stick times the length of that stick squared. Here it's 1/12 the mass times the length squared. And again, we really would need calculus to be able to show that. But if I take 1/3 and I divide it by 4, I get 1/12. So this here would have 1/4 as much inertia as this one did here. It would be 4 times easier to rotate that back and forth as it would if I held it there and tried to rotate it. Now I've already given you the equation of a ring rotating about this axis. It's this here. But if we rotate about that axis, it's going to be 1/2 mass times radius squared. It's going to be half as hard to spin it about this axis as it would be this other axis. All right, so I did say I was going to explain why this does it. Why does it flip-flop back and forth seemingly spontaneously? Okay, well, what we want to do is we want to look at the different axes that it could rotate about. One axis that it could rotate about is this axis here, so the whole thing's spinning like that. So I've drawn that same shape here so you can see it from a straight-on perspective. It could also rotate about this axis, and that's the one it was rotating about. So it could rotate where that little pipe connection piece there is right here, and it could spin like that. The third axis that it could rotate about is along this axis here. And here's that little small connection piece that's here, and it could rotate around like that. So 3 different axes it could rotate about. But now let's think which of these has the most rotational inertia and which is going to have the least. Let's do this one first here. This pipe here, the majority of that mass is right of that dark pipe there. It's really pretty close to the axis of rotation. Yes, there is some out there, but that didn't have that much mass. Most of the mass is right along the axis, so it has the least amount of rotational inertia. And then both of these were rotating so that the caps here on the end were really far away, and same thing here, really far away. But in addition to that, this piece had extra mass far away like that. So it's going to give this one more rotational inertia than this one. So rotating on this axis has the least, rotating on that axis has the most. That means this is going to be some intermediate value. And this is known as the intermediate axis theorem, that there's different axes that it could rotate about, but the one that had the intermediate amount of rotational inertia is going to be unstable. The axis that has the most and the least rotational inertia is going to rotate in a very stable way. And it is also known as the tennis racket theorem. If you've ever tossed a tennis racket up into the air, if you rotate around this axis here, it's going to be very stable. And if you rotate around this axis here, it's also going to be very stable. But if you rotate about this axis here, it's going to flip, and you won't be able to get it to just rotate about that axis. You can try it with a calculator or your cell phone. Be sure not to drop your cell phone, but you'll find that 2 axes, very stable, 1 axis, it's going to also rotate around the other axes as it tries to flip. All right, this is kind of a complicated problem, and it's absolutely more of the AP curriculum. So for sake of time, I'm not going to go through this actual problem. You can hit pause and look through it for yourself, but the question is, how much more rotational inertia does this have than this? And the answer is going to be 32 times as much rotational inertia. This is going to resist going faster, slower, or turning 32 times as much as this. And again, hit pause and work your way through that if you're in AP Physics 1. All right, so we said that these would drop and accelerate at the same rate, but they don't accelerate when they're rotating. And that's because the ratio of 2 things was going to be different. So we have to explain what those 2 things are. Well, when these are rolling down the ramp, they're rotating. Okay? So you can't just talk about how much force is making him go down that ramp, because different forces have more influence on how it rotates. And what I'm referring to is torque. Remember, if you put a force at a large distance from the pivot, that'd produce a lot of torque. And a force at a close distance to the pivot, less torque. This is Newton's second law with linear motion, but this is its equivalent with rotational motion. You can't just say how much force it had. You have to also calculate how much torque was on it. And you can't just plug in how much mass it had. You also had to do a calculation to figure out what the radius was and what the shape of it was. But the ratio of these two things would produce its angular acceleration. And back when we did circular motion, we found that if we measure this in radians and we multiply by the radius, we can get a distance along the arc. If we measure this in radians per second and multiplied by the radius, we could get a tangential velocity in meters per second. If we measure an angular acceleration in radians per second, and then multiply by the radius, we would get a tangential acceleration in meters per second squared. Okay, so just converting an angular to a tangential or a linear. So if we calculate its angular acceleration, we would just have to take the angular acceleration and multiply by the radius to get the tangential acceleration. All right, so let's see, well, what kind of torque is put on this ball? If we had a sphere on a ramp here, what is the torque that's causing this to rotate? Well, the ball is touching the ramp right there, and the center of gravity is right there, so gravity's pulling down as if it's all pulling down right in the center. Okay, so mass times gravity would be the force that's on that thing. Well, that force is acting at this distance. And so that's what's providing the torque. This force acting at this distance would be the torque. And we can measure that distance if we know the radius. This angle here is going to be the same as that angle there. So if I take the hypotenuse and I multiply by the sine of the angle, it would tell us what this opposite side is here. So this force times that distance would be the torque that's put on it. Okay? And if it was on a ramp that was less of an incline, a smaller angle, that's where it's touching. And we'll just do the same thing here. Gravity's pulling down with the same amount of force, but there's a smaller radius arm here, so there'd be less torque. Okay? Now, why did a large ball and a small ball accelerate at the same rate, regardless of size and regardless of mass? Well, let's calculate it here. The angular acceleration is going to be the sum of the torques, and the torque came from this, divided by how much rotational inertia it had. So this was the torque, it was the force, and r sine of theta is the distance. Because it is a sphere, the equation to calculate the inertia is 2/5 mass times radius squared. So looks like the mass cancels out. That a large object and a small object are going to accelerate at the same rate regardless of how much mass it had. And one of the r's on top is going to cancel out with one of the r's on the bottom. So again, a small sphere here and a large sphere here is going to have the same angular acceleration regardless of mass. But the radius is going to change how much it accelerates angularly. This ball here had the smaller radius, so a smaller radius in the denominator, it's going to have a larger angular acceleration. Okay, the number of radians per second. But remember, we can convert an angular acceleration into a tangential acceleration by just multiplying by the radius. So we're going to take that angular acceleration and multiply by the radius. Now there's a radius on top and a radius on the bottom. Both of these balls, the rim of this ball the tangential part of it is going to have the same acceleration regardless of mass and regardless of acceleration. As long as the acceleration of the gravity is the same and the angle is the same and the shape of the object, 5/2 came from 2/5 being a sphere, they will have the same tangential acceleration. All right, now let's see if this is a kind of a complicated problem, but I do want to work through this. Here we have a mass hanging from a string that is wrapped around this very large, we're going to call it a disk. It looks maybe like it has more mass along the rim, but let's just say the mass is evenly distributed. Well, we have to understand the relationship between the tangential acceleration and the angular acceleration. If this moves this little distance here, rotating through an angle, this thing's going to drop that same distance. And the next moment in time, it's going to go through a bigger angle. It's going to be a bigger distance, dropping further, bigger and bigger and bigger. But just the distance along that arc and the distance it drops are going to be the same. Okay. Now, if this had very little rotational inertia, this thing would just zip down really fast. If this had a lot of rotational inertia, well, it would be pulling against a lot more resistance and it would accelerate a lot slower. So that's going to affect how much tension is in that rope there. So we're going to go ahead and take this piece here because we have to convert an angular acceleration into a tangential acceleration. But we can calculate the angular acceleration by how much torque was put on this tension times that distance, and then the rotational inertia. So the tension times the radius is the torque. It is a disk, so it's 1/2 the mass of that large one divided by the radius squared. And then when I take that and multiply by the radius, this radius here, I get the acceleration. So it is going to have the same acceleration regardless of the radius. Okay. So now I'm solving for t. I'm going to take the 1/2 of L and move it to this side. There's two variables, the acceleration and the tension. So we need a second equation. Let's go ahead and use not this Newton's second law for rotation, but Newton's second law for linear motion. This is going to be accelerating in a line. It is going to have downward acceleration, so I needed to make that negative. The tension is pulling up, mass and gravity, the weight of it is pulling down, so we're subtracting those two things. That's the sum of the forces divided by the mass equals the acceleration. And I'm substituting this here into the tension, so that's what goes right there. Now I'm going to do two things. I'm going to forget this for a second, so it's just this equaling this. I'm going to take this and multiply by both sides, so it's going to show up over here. And this term I'm going to subtract from both sides, and that's going to show up as a negative over here. There's a negative in every term, so I can just multiply by -1. Everything becomes positive. And then I'm also going to say there's an acceleration here and an acceleration there, so I'm going to factor it out. Now I'm trying to solve for the acceleration. I divide both sides by that. So I can calculate the acceleration of this if I know the mass of the small and gravity, the mass of the small and the mass of the large. I do know those things, so this is the acceleration of that object. Okay? If it had more mass, if this had more mass, it would have had less acceleration. It would have had more rotational inertia. Okay? And again, that might be a good one to pause on and work through the math that I just showed. Now, an interesting example here is if a big smokestack chimney like this were to be demolished and tip over. Okay, so we blow out the base and it tips over, and watch what happens as it falls. As it falls, it breaks up. And that's because of this equation right here. That it broke up on the way down, but if it didn't break up on the way down, and it maintained a solid shape there, it's going to, every part on that smokestack is going to have the same angular acceleration. So at this radius, it's going to have some tangential acceleration. At twice that radius, it would have twice the acceleration, and at 3 times that radius, it'd have 3 times the acceleration. But the angular acceleration was the same for every piece on there. So the further and further and further and further you go out, the greater and greater it's accelerating tangentially right there. So there's that same idea here, and let's explain it this way. This is a ball that is on a little golf tee. This board is hinged right here, and that whole thing is going to move with the same angular acceleration at every radius. But bigger radii are going to have a greater tangential acceleration. Okay? There's going to be some point along the distance here where the tangential acceleration is the same as the acceleration of gravity. And let's just drop that and see what happens. Boop. Okay, it happened kind of fast, but let's look at it in slow motion here. Ball falls straight down. The cup got to the bottom before the ball did, which means the ball was accelerating slower than the cup. Okay, so there it goes again. Right there, the cup got there before there. So let's calculate what that should be, and we're going to do it with a different example. In this example, I have a meter stick here, and I took a table saw and very carefully cut a groove right along that thin edge of the meter stick so that marbles can rest right on that edge. And I made a little hinge here, and I'm holding it over here. I'm going to let go of this, and that whole meter stick is going to rotate with some angular acceleration. Okay, so the angular acceleration for every part of that meter stick is going to be the same, but different radii are going to have different tangential accelerations. I want to know at what radius will the tangential acceleration be the same as the acceleration of gravity. And remember, for a stick rotating about its end, the amount of rotational inertia it has is just 1/3 the mass of that stick times the length of that stick squared. So let's calculate the acceleration, the angular acceleration. For that stick, we're going to say that the center of mass is right in its middle, pulling down, and that force is acting at a distance that is half the length of that stick. The center of gravity is right in its middle. Okay, so force times distance is going to be the torque that's put on it. The amount of rotational inertia is 1/3 mass times length squared. That was for any stick pivoting on its end. And it looks like the mass is going to cancel, and the length is going to cancel with one of the lengths on the bottom. I have 1/2 in the numerator and 1/3 in the denominator. We can copy dot flop, and we get 3g over 2l. If we solve this equation here for a, or alpha, it's going to be the acceleration divided by the radius is going to be the angular acceleration. Remember, we're trying to find out at what radius the acceleration would be the same as the gravity. So let's take that piece there and solve for r. The question is, at what radius will the acceleration be the same as gravity? So when a equals g will be our answer. So we're going to let a equal g and see it cancels, and it looks like the radius is going to be 2/3 the overall length. So that distance there is what's going to be falling at a rate equal to gravity. So at 66.6 repeating centimeters, that place is going to fall faster than gravity, which means places further out are going to be falling as fast as gravity. Places falling further out will fall faster than gravity, and the meter stick closer in is going to be going less than gravity. So when I drop this from this end, these balls here are not attached to it. They're just going to want to fall as fast as gravity. So they just fell as fast as gravity right there, and we can see that it got further away there. Now, I predicted that this spot, 66.6 centimeters, would be falling as fast as gravity, but it looks like about right here is the transition between those two. And the reason is we assumed that the center of gravity was right there at 50 centimeters. And that's true if we were looking at just the meter stick. And it was true when all those balls were touching the meter stick up at the top here. But the moment we let go of it, those marbles aren't touching the meter stick, and these are. So this is pushing down on this side more than what was over here, and it's going to shift the center of mass a little further that way. Okay, and so the distance here is going to be changed as well. Anyway, that's a little bit about rotational inertia. It has to do with where the mass is and how it's distributed. The further from the axis, the more rotational inertia. Closer in, less rotational inertia. And then the angular acceleration is the sum of the torques divided by the rotational inertia.